Okay, hello everybody. Good evening. Our last class. Yay. Few words about the test. Do not make the mistake of thinking you're ready for the test. Okay? You've done a lot of homework. You've worked very hard. I know you worked hard. I've seen the results. Most people are in very good condition, except for those who are constantly copying from their friends. But most of you are in very good condition. You're in the stage that you will pass the test. So if you did the homework correctly, if you did it properly, if you did it by yourself, I'm pretty confident that you'll pass the test. But in the same way, I'm also confident that you will not get a very good grade. You'll get like a 70. If you want to get a good grade, first of all, go over the theory again, go over the homework again, go over the tutorials again. Notice that many of the homeworks, there were a lot of sections giving you how to solve it, telling you each step was very little, was very small, but in total the question was long. In the test, you will get similar questions, but with less subsections. So make sure you understand how to tackle a question without getting all of the different subsections. So when you go over the homework a second time, maybe try just reading don't read everything again. Just read the main question, and then try to solve without having all the subsections. Because you need to understand how to, by yourself, know how to solve questions. Right, so for instance, you're giving the initial wave function and you automatically ask to find a mean value as a function of time. Then you have to know that first of all you have to go to the energy eigenbasis, and then you have to advance in time, and then you have to take the bracket. And you're not told in the subjects to do it like in the homework. So make sure you know how to tackle questions. That's the most important thing. When you've gone over the homework and you're sure you know how to do that, you can go look at Eli's previous tests. They're all in Hebrew, but maybe your friends will translate them for you. But on Eli's website, search Eli Barkai in Google, you'll find his website. He has a bunch of previous tests for quantum mechanics. So you can look at his previous tests. That's definitely a good way to start studying. And if you want, he already told you this, you can look at different universities around the world. Maybe you'll find some interesting good questions. Let me know. That's also a way to get ready for the test. We need a equation sheet. As I told you, I started making something, but I'll need to consult with a couple of you. It's a small litigation. So maybe some people want to meet with me, say Sunday or something like that. That would be a good idea, because by Monday or so we'll be handing in the test to the Department of Tests, and then it will be too late. So if you really want an equation sheet and you want to go over it before I suggest we meet on Sunday, so be in contact with me, or at least some of you. Questions before we start this lecture? Okay, so calm down now. We're finished by the test. Let's do some physics. This is for later. That's going to be exciting. First of all, I want to go over a little bit more hydrogen stuff. I want to solve a question for the hydrogen atom. The question we'd like to solve, we would like to find the probability that the electron can be inside the nucleus. Up until now, we always talked about the nucleus as a point-like particle, which generates the potential, the Coulomb potential. But we know that the nucleus of an atom is actually finite. There's a certain size, a certain volume. It's very small. I'll give you numbers soon. But that means that there's a probability, or there might be a probability, that the wave function is inside the nucleus. It's quantum mechanics. Such stuff is possible. We would like to find the probability that the electron is inside the nucleus. We will assume that the nucleus is a ball, a sphere, of radius b. And we will calculate this probability for the ground state of the hydrogen atom. for the ground state. So the first thing we need to know is the wave function of the ground state. What are the quantum numbers of the ground state?
1, 0.
1, 0, 0. This is very important to know. The ground state is spherically symmetric. Depends only on r, not on theta and phi. And it is equal in position space to 1 over root pi AB to the third. AB is the Bohr radius. E to the minus r divided by AB. This is given. So obviously this is quite a simple question. What we have to do is find the probability to be inside the nucleus. So to be at r smaller than b. So this is the integral in 3 dimensions, d3r on psi squared. And when we break this down, there are 2 integrals. An integral dr r squared. It's not over the entire space. It's kind of misleading here. The integral over it's the integral over the nucleus. So the integral in the r direction is from 0 to b. Of this function here. So it's psi squared, so there's no more square root. And then there's an integral over the angles, but obviously the integral over the angles, since it is independent of the angle, it's just 4 pi. So now we can compute this integral. Now this is an integral of r squared times an exponential function. This is done by integration by parts. So I won't do all the math here now, but of course you need to know how to do it. I'll just give you the solution. So you find this is 1 minus 1 plus 2b divided by ab plus 2b divided by ab squared. That's the 3 terms from the, because you need to do integration by parts twice, to the r squared. Then there's one more, and then there's one more term from the last integral. And all this is multiplied by e to the minus 2b divided by the Bohr radius. So this is an exact solution. Now we can take a limit, and then the limit that the nucleus is much smaller than the atom. The atom is mainly vacuum. There's a little electron, which as far as we know is point-like. Actually, there is no measurement. This is real physics, right? There's no measurement telling us the size of the electron. As far as we know, the electron is point-like. In other words, it is smaller than anything that has ever been measured. So we only know an upper bound to the size of the electron. We do not know to the present day how large the electron is. For the nucleus, we do know a size. The nucleus is about 10 to the minus 15 meters in radius. We know that the atom has approximately the radius of the Bohr radius, so about 10 to the minus 10 meters, an angstrom, or half an angstrom. So B is much smaller, about 5 orders of magnitude smaller than A. So we can take the limit where B over A is very small, much smaller than 1, and obtain an approximate formula. So we'll take the limit where B over AB is much smaller than 1. And in this limit, we can expand the exponent in a Taylor series. So when we do this, we get this same brackets in the beginning, and then the Taylor series of the exponent 1 minus 2b over ab minus plus, right? And then my Taylor series plus 2 there's a 1 over 2 from the Taylor series, right? And then there's a 1 over 3 factorial here. So 1 over 6, and then that cancels with the 2 to the third, which is 8. Right? So 8 divided by 6 is 4 divided by 3. Right? It's from the Taylor series. B over AB to the third, and so on. Right? So this is our Taylor series. And now we can factorize these brackets. And we'll be interested, usually when you take a limit, you're interested in keeping the leading order. Leading order is the lowest power that doesn't cancel. So next step is to multiply here and keep leading order. So let's multiply out these brackets with a lot of terms. So we find the probability is around approximately equal to 1 minus 2b over a plus 2b over a squared minus 4 divided by 3 b over a to the third. That was 1 times this. Now I'm going to do 2 times this thing. So I get 2b over a minus 4b over ab squared plus 4b over ab to the third. I won't take to the fourth because I know that the third power will be the leading order. If you didn't know that, just take another couple of terms and just to be sure. Now I have to multiply the third term here by all of these terms. So I'll multiply just by the first two and neglect fourth power and above. Now if you take a look at this, as I promised, this will cancel with this. So the first order, b over ab, cancels. That would be, but the leading order would be 1, but as a 1 minus 1, so that cancels, right? Then the next order would be the first power, but that cancels as well. Remember, b over a is a small parameter, b over a is much smaller than 1. The next order would be b squared, but we have 2 of them, minus 4 plus 2. So they also cancel. And we remain with the third power. That's the first order that doesn't cancel, so that's the leading order. So we find that this is equal to 4 over 3 b over ab to the third. This is an approximate formula, which is also a little bit easier to interpret than the exponential, because you don't really have an imagination for this. But here you see that the probability goes like the ratio to the third. So it's much easier to interpret, and in this limit, it is also quite accurate. Now I want to show you a different way to calculate the same probability. And then we'll compare the two answers. And it's different. It's the physical idea behind this calculation is different. So the physical idea is the following. Because the nucleus is so small, it's much smaller than the radius of the atom, I'm going to assume that the wave function of the electron is constant within the nucleus. So if you think of the entire atom is this big thing, this is the atom, and the nucleus is this little thing in the middle. So I'm going to assume that over this area, or this volume, the wave function is constant and equal to its value at r equals 0. Okay, so for r smaller than b, smaller than the radius of the nucleus, we can assume that psi just equals its value at r equals 0. And when we do this approximation, then the probability to be inside the nucleus is now, again, the integral over the volume of the nucleus of this psi squared, but the psi is constant. So we can take it outside the integral, which is a constant, right, times this volume integral, and now because it's just integral over 1 over the dimensions of the nucleus, it is just the volume itself of the nucleus. So it's 4 pi over 3 e to the third. Yes, it's clear? And psi squared, it's its value at r equals 0, and you see here that the value at r equals 0 is just the normalization constant, and that thing squared is 1 over pi a to the third. So when you multiply these two terms, you get 4 third b over a to the third. Familiar? So you see that if you take the exact solution and then keep just the leading order, it is the same as assuming that the wave function is constant within the nucleus. It's a different physical idea. Here I first taught you the exact solution and then approximated. And here I, from the beginning, took an approximation. But mathematically, it turns out to be the same. So that's a nice way of thinking about physics. You get there in two different ways. Let's plug in some numbers so we get a feeling for this probability. So I told you that B is approximately 10 to the minus 15 meters. It's a femtometer. We know that the Bohr radius is about 0.5 angstrom. So if we plug in these numbers here, then we get like 10 to the minus 15, right? 32 divided by 3. It's about 10, more or less, times 10 to the minus 15. So it's about 10 to the minus 14. So the probability of the electron being inside the nucleus is really small, vanishingly small, because the nucleus is so small. But of course, it's not zero. Quantum mechanics, anything's possible. Just wait long enough. But let's just so you get an idea for the for this value. Okay, questions? Okay, let's look at a different. One more thing I would like to show you in the hydrogen atom, or generally in angle for spherical coordinates. So we will again consider the ground state of the hydrogen atom. Usually we ask the question, what is the probability of being a distance r from the nucleus? But now I would like to ask the question, what is the probability, let's keep this, what is the probability of being at a certain angle theta? For the ground state of hydrogen atom, which is this, find P of theta. So what is the probability to be within a certain angle? So obviously the probability to be at a certain point in space, which is defined by 3 coordinates, is just psi squared, right? So P psi 1, 0, 0 squared. Then as an r squared sine theta dr theta d phi. Volume element. Now since I'm asking for a probability to be at a certain angle, I have to integrate over the radius and I have to integrate over phi. Okay, let's do so. P of theta. So I'm not integrating over theta. Let's take all the theta dependents outside. So we get a sine theta d theta. And then I can also take out the normalization. So divided by pi a b to the third. And then there's an integral d phi, which stands for itself. I'll just give 2 pi. And then there's an integral dr r squared e to the minus r divided by ab. 2 of them squared from 0 to infinity. I'm integrating over the entire space in the r direction. This integral can be computed. Again, integration by parts is the way to go here. This time, of course, it is much easier because this time your boundary terms will vanish due to the infinity up here. In the previous question, we had a b up here, the boundary terms didn't vanish. In this case, the boundary terms either vanish, they vanish when you put in 0 because of the r, and they vanish because, and infinity because of the e to the minus r. Right? A polynomial times an exponential, a decaying exponential, and infinity is 0 because it decays faster than this grows. Take the limit and see that. So you only get one term when you calculate this integral, which is ab to the third divided by 4. So in total you find, right, the ab cancels. Of course it must be dimensionless, it's a probability, and you find 1/2 sine theta d theta. Right, the pi cancels, the ab cancels. Where did 1/2 come from? That is a 2 divided by 4, that's 1/2, right? Now what's weird about this? Or maybe it's not weird. But notice that the wave function is independent of theta. But the probability depends on theta. So it's a wave function which is spherically symmetric. It doesn't matter in which direction you look, you see the same wave function. You don't see the wave function because it's a wave function, but you know what I mean? But if you look at the probability, it depends on theta. How is that possible? So this is one of the problems with spherical coordinates. What depends on theta is not the wave function, it's space itself. Think about looking at a certain position in space. So we were looking, right, if we're situated here at the center, and we're looking what is probability to be within some angle d theta. Right, this is theta, and then we're looking for the probability to be inside this angle d theta. So the extent of this angle depends on where you're looking. For instance, if you look, it's three-dimensional, right? So you have to take this and rotate it around the z-axis. So if I'm looking at the horizon, then it's this entire plane. But if I'm looking up, it's just a cone. So obviously a cone has less volume than the entire horizon. See what I'm saying? No. Looking from above, okay? So the z-axis is coming out at you. It's a vector coming out at you, it's the z-axis. So if I'm asking what is the probability to be at theta equals, the same place. What is the probability of being at theta equals pi over 2? So what do I mean by pi over 2? It's the board, right? If this, on the other side, on the other hand, I'm asking you, this is that axis, I'm asking you what is the probability to be at theta equals 0? It's a line coming out at you, right? So the probability to be inside this plane is obviously larger than probability to be inside this line. So it depends on theta is space, not the wave function. Okay?
So it depends how you look at it.
What do you mean?
If you look from above, it looks like a point. But if you look from another side, it looks different.
It's not a point, it's a line. It's a line coming out at you. Think in three dimensions.
If you
I
look
can't
from
draw it.
above.
Yeah, also if you look from the side, if this is the z-axis, in this case, right, this is the z-axis, then theta equals pi over 2 is the plane coming out at you, right? And in this case, theta equals 0 is the z-axis itself. So I figured it would be easier to think about it from above, but obviously it's the same thing. It doesn't matter where you look at it from. Right? You can move it in your mind however you want. But my main point is that this theta is due to the space. Space depends on theta, not the wave function, right? So the probability to be inside a certain area changes because the element changes. This is the same reason that we have, of course, a Jacobian. This is the reason there's a Jacobian for spherical coordinates, and there's not for Cartesian coordinates, because this problem doesn't arise in Cartesian coordinates. So when you move to spherical coordinates, watch out, make sure you understand what you're talking about. Questions? Okay, cool. It's time for a demonstration. This is what I wanted to point out for the hydrogen atom. One more tip that I can give you for life is really think about your coordinates. Think about spherical and also cylindrical coordinates and what they actually mean. Give you something to think about. In order to, if you talk about Cartesian coordinates, so x, y, and z, then you usually need to define a point in space. You need 3 coordinates. You need to specify your x coordinate, your y coordinate, and your z coordinate. If I tell you only x equals 0, I say nothing about y and z, then you're in a plane, not a point, right? So I have to define x equals 0, y equals 0, and z equals 0 in order to define a point. But in spherical coordinates, there are special points. If I tell you r equals 0, I say nothing about theta, nothing about phi, you know you're in a point, not a plane. If I tell you theta equals 0, I tell you nothing about r and nothing about phi, you know you're on a line. But in Cartesian coordinates, you need 2 coordinates to define the line, not 1. So spherical coordinates sort of make special points in space. They're not special for, they're special for nothing. Doesn't mean that I'm in the center of the world just because I choose r equals 0 where I'm standing. But I sort of make it a special point in space because of the choice of variables. Okay, so that's something to dwell about.
By the way, what's the real probability?
Excuse me?
What's the real probability for P theta?
Well, plug in theta and you'll know it. Depends now. If you're looking at theta equals 0, then the probability is 0, because sine theta is 0.
So this is the probability, but it does not come because of the wave function, but because of how we look on space.
No, what do you mean? You can transfer this into Cartesian coordinates if you want. You know how to go from spherical to Cartesian coordinates. So you can plug in theta in Cartesian coordinates. I never tried it. Might be interesting. But sine theta is z divided by the radius. It's the sine. So it's r sine theta divided by the radius. It's more complicated, but you can do it. You can plug it. You can bring this to Cartesian coordinates and take a look at it. But it shows you that the probability of being on the line, right, is 0. And the probability of being on the equator is 1/2. That's what you see from plugging in numbers. You can also verify, by the way, obviously, that the integral from 0 to pi over p theta this equals 1, which must be true. Okay, demonstration. So what I want to discuss is a 2-level system. And I hope that, I'll show animation first, I hope this will make these, remember your homework and what we solved in class with these molecule and the electron jumping around from atoms, and then we added interactions and so on, and the Hamiltonian changed. So I'm trying to demonstrate with classical analogy what this means. What are these interaction terms? Why does the Hamiltonian change? Why do the eigenstates change, and so on? So I'll demonstrate this with a two-level system or a three-level system, but of course the physics is the same. And that's what we're going to use classical analogy for, because these kind of states is not just it's not just in quantum physics, also just in classical physics, which don't think about it that way. So I'm going to start with two harmonic oscillators, two pendulums, and these pendulums have the same length. My drawings don't, but the same length and the same gravitational force, which means that the frequency at which they'll oscillate will be the same. Right? So let's call that omega naught. So this is the easy part of the demonstration. This is omega naught, right? Just going back and forth. And the second one will go back and forth with the same frequency. Let's read that one as well. So I'm going to now introduce the language of quantum mechanics. I'm going to call it state A when this left pendulum is moving. And I'm going to call it state B when the right one is moving. Okay, so if the system is this entire block, then this is state A. Now the system is in state A. And now the system is in state B. Of course, I can also do something like this. Now the system is in a superposition of A and B. Right? Are you with me? It's analogy to quantum mechanics. What we're looking at is the wave function. Obviously, you can observe wave functions, and that's where the analogy breaks down. But this is what I'm saying. State A, state B, and I can excite either one or a superposition of the two states. So the Hamiltonian of the system we know that if there's a frequency omega 0, then the energy, this is where I'm using the analogy again, is h bar omega 0. And because they both have the same frequency, it's the same value. So the system is degenerate. And the off-diagonal elements are 0 because these are eigenstates. If I excite just the state A, then state A will continue to be excited, it's a stationary state, and state B will never start moving. Okay? So A and B are eigenstates of this Hamiltonian. Okay, that's what I mean by stationary state. You excite one of them, and its evolution in time is just this e to the power I whatever, take it squared, it drops out, stationary state, nothing changes. So if you excite one of the states, it does not affect anything else. That's why this Hamiltonian is diagonal. Right? State A would be represented in this basis by 1, 0, and state B by 0, 1. Right? Now, what happens if we add an interaction? So what I'm going to do next, so the new board, so I'm going to add a spring between two pendulums. So we have two pendulums. Both have an eigenfrequency omega naught. And now I'm adding a spring. It has some spring constant, and that spring constant will define the strength of the interaction. That's obvious. And I'm going to express it in units of frequency and call it delta, such that the energy of the interaction is h bar delta. Now this means that state A interacts with state B, and state B interacts with state A, and the energy of interaction is h bar delta. That means that the Hamiltonian is no longer diagonal. We have on the diagonals of the energies, but on the off diagonals we have these interaction terms, h bar delta. We can now use these to find the new eigenstates and the new eigenenergies. Right, when we do this, let me just demonstrate this first. So when I add the interaction, I had an interaction here somewhere. There we go. There it is. So I add an interaction, right? If I now excite just this mode, this side. It worked yesterday. So it's tired. So I excite just one state, and you see the second state starts moving as well. Right? This is called beating in classical physics. You've seen this one before, I hope. I really hope you've seen this experiment before, because it's a classical experiment. It's both classical and classical. You see now these states A and B are no more eigenstates of the system. So what are the eigenstates? So let's diagonalize this Hamiltonian. So let's take out the h bar and just talk in terms of frequencies. The eigenvalue is omega. And this is just h bar times this. So I can diagonalize this matrix and then multiply the eigenvalues by h bar. It's the same thing as diagonalizing this. Just saving a little writing. So this determinant is omega naught minus omega squared minus delta squared. This must equal 0. So we find that omega equals omega naught plus minus delta, right? Hope I'm not confused.
Yes.
I'll be confused when I'm doing an action. Yeah, that seems right. Oh, well, minus plus, I guess, but whatever. So there are two omegas, let's call them omega plus and omega minus, two modes. And the frequencies are omega 0 plus delta and omega 0 minus delta. The frequencies and the energies are h bar times that value. So if you now look at the energy, what happened to the energy? Here is no interaction. So delta equals 0. And here is with interaction. So delta larger than 0. So here we have two degenerate states. And here we have two non-degenerate states. This value here was omega naught. And the distance between these two here is 2 delta. Right, so distance from the middle, this is delta, and this is, well, h bar delta. This h bar omega 0. Right? So the interaction destroyed the degeneracy. Degeneracy is lifted. Okay, now that we have the eigenvalues, we can find the eigenstates. Mathematics is not very difficult here. So for omega plus, for omega equals omega plus, put it back into the equation. So we have omega 0 minus omega 0 minus delta. So there's a minus delta, delta, delta minus delta, and sum xy equals 0, so x must equal y. So the eigenstate associated with omega plus, which I'll just call the ket of plus, right, it's the symbol, is 1 over root 2, 1, 1. On the other hand, for omega equals omega minus, this matrix becomes just a bunch of deltas, which means that x must equal minus y, which means that the minus state is 1 over root 2, 1 minus 1. Of course, this can be written in terms of the eigenstates a and b. So this one is 1 over root 2 a plus b. And this one is 1 over root 2 a minus b. So if I excite both states together, either without a phase or with a phase, what is minus? E to the I pi, right? It's like saying, this is like saying plus e to the I pi b. So if I excite them without a phase, or with a phase of pi 180 degrees between them, that will be an eigenstate. So you all know obviously the two eigenstates. So if I excite them without a phase, which means I give them the same amplitude, they'll go back and forth together. That's an eigenstate, a stationary state. Hope you can all see it. And the other one is if I excite them with a phase of pi. So I pull them both out, and then I'm going like this. That's also an eigenstate. That's a stationary state. So these are the new stationary state of the system. I've added interaction. The states A and B, which intuitively make sense, just this or just this, are no longer eigenstates. But there are other eigenstates. They're just a little more complicated. There's this one, and there's this one. Okay? So it's very simple how to think about this. And of course, the frequencies now are different. It's a little hard to see on the simple model, but the frequencies at which they oscillate are different. This one is much faster than this one. Or not much faster, but if delta were large, so if you use the strong spring, then obviously this will be much larger because the spring is actually working. Right? It's pulling them together. In this case, the spring isn't doing anything because they're going springs over the same length. But here the spring is working, so obviously this one is much faster if the spring is very strong. All I wanted to say. Right, so now let's look at the typical question. What happens if we start a system in A? Well, you know the answer for the oscillator, but we always solve this question at what happens if we start with psi naught equals A. So in this state, right, where it's just one of them is excited, what happens for later times? What is the wave function of later times? So you know how to solve this question. What you have to do is write the wave function in the eigenbasis of the energy. So since we know that this plus state is A plus B and the minus state is A minus B, so obviously if we take the plus state plus the minus state, the B's will drop out. Right? If I take this plus state plus the minus state, then I'll get 1 over root 2 A, and then plus B, and here I'll get 1 over root 2 minus B, so I'll drop out, and there's another one of these, so it's 2 times this, which means that A is 1 over root 2 the plus state plus the minus state. So this is psi naught. This means that psi of t for later times is 1 over root 2 e to the, what do I call it? Omega 1, right? Omega plus. E to the minus I omega plus t times the plus state, plus 1 over root 2 e to the minus I omega minus t times the minus state. So we know what omega plus and omega minus are. That's what we found when they diagonalized. And now you see that they evolve as a function of time. We can pull them out. I did some mathematicals. Right, okay. So there's an important step I want to talk about now. So now we're working the energy eigenbasis, right? It's a very unintuitive basis. It means that we're sort of in a superposition of this state and this state, right? It's very unintuitive to think about this basis. So what we want to do is go back to the intuitive basis AB. Because I know that in this basis I know exactly what they all mean. So how do I do this? I plug in these values, right? The definition of plus in terms of A and B into here, and the definition of minus in terms of A and B into this minus. So when I do so, I'll get 1/2 e to the I omega plus minus I omega plus A plus B. Plus 1/2 e to the minus I omega minus t. And for the minus I get A minus B. And then we can group the A's together and the B's together. And take out common factors and try and find something that we can understand, not exponentials. Obviously we'll be able to generate cosines and sines. So I'm preparing you also for your mechanics test simultaneously. So you know how to do that as well. So when I group them together, right, we find psi of t is now equal to 1/2 e to the minus I omega plus t plus e to the minus I omega minus t. A plus 1/2 e to the minus I omega plus t minus e to the minus t times the B state. So the difference is the plus sign and the minus sign between the exponentials. And of course this up to a phase, this will become a cosine and this will become a sine. And we know that global phases aren't relevant. You can check that if you're adding or subtracting two exponential to complex exponentials, then you do this trick where you take out half of the alpha and half of the beta, and then you make these two the same up to complex conjugation. When you do this game, then you find that this is equal to e to the I beta times e to the I alpha minus beta divided by 2. It's just stupid way of writing this. It's just plus here, right? E to the I plus beta over 2 times e to the I alpha minus beta divided by 2 plus or minus e to the minus I alpha minus beta divided by 2. So this is just a constant phase, which we don't care about. And this is either a cosine or a sine, depending on the plus or the minus here. So in virtue of this identity, which is really easy to obtain, you can write this as the cosine up to phase factor, which is relevant, and then the 2 that comes out of the cosine will cancel this 2. So it's the cosine of omega plus minus omega minus divided by 2 times t times the a function plus the sine of the b function, the b state. So first of all, you obviously see that this is normalized to 1. Cosine squared plus sine squared is 1. So you see it automatically, that's evident. And you see that now the probability of being in state A or in state B is a sinusoidal function. And that's what you saw in the demonstration. I start just one of them, but it now goes to 0. You see now it's 0, and it's coming back up again. Now it's 1 again. And it's going back to 0. And it's coming back up again. That's its cosine, or sine, whatever. In terms of classical physics, it's the energy exchange. The energy is going from one pendulum to the other through the spring. That's interpretation on classical level. On a quantum level, this is the interpretation. It's the wave function that oscillates back and forth at the intermediate frequency. Okay? Questions about this? Okay, so I hope you understand eigenstates a little bit better. And you have gained some intuition. So move on to a different topic. I want to clean up some odds and ends before I send you on your way to get a good grade in the test, which I'm sure you all will. I want to clean up some odds and ends, things that might be unclear, maybe they are, maybe they're unclear. So before we get there, before we get to the test, hope I can clear up some stuff. So I want to take you back to the free particle. Remember, in the free particle, our eigenstates depended on some quantum number k. This k was not quantized because there are no boundary conditions. And it was equal to, say, in 1D, 1 over 2 pi, 1 over root 2 pi e to the ikx. And then we had a problem, right? Because now we wanted to look at the inner product, k prime k. And we said, okay, that is now 1 over 2 pi times the integral e to the I k minus k prime x integral from minus infinity to infinity. And we saw this actually diverges. It's 0 if k is different than k prime. But if k equals k prime, then this thing is 0. And then I'm integrating over 1. Right? E to the power of 0 is 1. So I'm integrating over 1 from minus into plus infinity, and it diverges. So this thing, where k equals k prime, diverges. So it couldn't be normalized. We saw this in the same fashion when we tried to calculate the probability to be at a certain position. We saw it was equal in all space. And again, it can't be normalized because the sum over an infinite constant number, right, is obviously infinite. So it couldn't be normalized. So the way to solve this problem is just put your free particle in the box. But not just any box, you want to put it in a very large board, in a very large box. So let's assume that the particle is confined, it's 1D, so let's assume it's confined to a line of length L. And we're going to assume periodic boundary conditions. Periodic boundary conditions means that when the particle gets to L, it suddenly is beamed back to 0. So it's like living in a ring. If you're living in a ring, you'd never know it's a ring unless you walk around and find yourself in the same place again. If you're a one-dimensional particle, you're living on a ring, right? The only reason we can think about a ring is because we know what 2 dimensions are. But if you don't know what 2 dimensions are, and you only know what 1 dimension is, you wouldn't realize you're living on a ring until you walked around once. See what I'm saying?
It would be like those video games that you go out and you come back in the...
Yeah, it's like Snake. That's just a one-dimensional case of Snake. That's for the old people amongst us. New people don't know what Snake is. But people used to have a Nokia phone, right? Black and white. They know what Snake is. It means that if you're in 2 dimensions, you can think about it in 2 dimensions as well. If you just live on a plane, so you're living on the table, right? And you can walk left and right. You can walk back and forth, but you cannot go up and down. You don't even know what up and down means. So you can walk in all the directions. But now imagine that instead of living on a table, you're living on the surface of a sphere. Again, you can just walk left and right and forwards and backwards. You cannot go up and down. So you wouldn't realize that you're on a sphere until you walked around once and came back to the same place. Because if you just walk from here to here, it's the same thing as walking on the table in a straight line. We never notice it. The only reason you can imagine a sphere is because you know what 3 dimensions are. So you take this 2-dimensional surface, sort of the sphere, and you embed it in 3 dimensions. And now you know what 3 dimensions are. Right?
Right.
This is why 3 dimensions, by the way, can also be periodic. So it's possible in 3-dimensional space, in the universe, that I go in one direction forever, not forever, and after a certain time I'll come back to where I am. That is the case if I am living on the surface of a 4-dimensional sphere. This we can't imagine. I'm getting off topic. It's not quantum mechanics anymore, but it's interesting physics. We just missed the most interesting part. It's true. Right? And that's what's called a closed universe, by the way. So that's why I think of topics, it's cosmology and quantum mechanics. But it's something interesting to think about. So we're imagining a particle which lives on a ring, but the particle doesn't know it's on a ring unless it goes around once. So we're imagining periodic boundary conditions. Periodic boundary conditions means that the wave function must be equal to itself if it goes around once. If it travels distance L, it must be equal to itself. But we're going to take the limit where L goes to infinity. You'll see why this is important in a moment. So if we do this, we solve the Schrödinger equation. So we find that the solution for the eigenfunctions are e to the ikx. Or e to the minus ikx, but let's just look at e to the ikx. Not normalizing yet. Okay, we're going to normalize in a second. We're going to normalize yet. First, we have to impose our boundary conditions. So this is the solution to the Schrödinger equation. Now we impose the boundary conditions. So e to the, they're true for any x, so we might as well do for x equals 0. Or we can do for general x if you really want to. So e to the ikx is equal to e to the ikx plus L. So we find that 1 is equal to e to the ikl, right? Because we can cancel e to the ikx. And from here we get that kl must equal 0. Must equal n pi, sorry, must be equal to 2 n pi divided by L.
No, KL. Either you don't write KL or you don't divide by L.
What?
No n.
No, it's KL equals 2 n pi or K equals 2 n pi over L.
Right. Yeah, so KL equals 2 n pi, right? Sorry, I'm going myself. So KL must equal 2 n pi. Either it's 0, or it's 2 pi, or it's 4 pi, right? This exponent, and then it's equal to 1. So we found in this case that k is quantized. Unlike this case, where k was a continuous number, it is now quantized. This happened because we put the product in a box. But remember, we're taking the limit where L goes into infinity. The difference between two k's, so delta k, which is, so this is kn, right? It's quantized. So delta k is what I'll call kn plus 1 minus kn. Now this is just 2 pi over L. This might look familiar to you from thermodynamics. Maybe not. Density of states? No, that's next year? Okay, never mind. So delta K is the difference, forget what I said. Delta K is the difference between two following Ks. So it's 2 pi over L, and the limit where L goes to infinity, this difference is very, very small. So it's almost continuous. So if you make L large enough, the question always is, I'm saying it's very small compared to what? So it depends what you're measuring. So if you can only measure K up to a certain scale, because you're limited by measuring devices, then you can make L large enough that this delta K is smaller than your measuring scale, and then it's irrelevant, because it looks continuous to you. Right? It's like in a computer screen with a lot of pixels. If you look far enough away, there are enough pixels, it looks continuous to you. But you know it's actually quantized in pixels. So it's the same idea. If you're looking at a big enough scale, then you can choose, if you look at depending on your scale, you can choose L large enough to make this irrelevant, and it's actually more or less continuous. And now we can normalize our wave functions together with this condition. So now we want to take our wave functions and normalize them. So we need to take the integral from 0 to L. That's the main difference now. It's not to infinity, it's to L, because that's our entire world. We're inside a box, or a line in the 1D case. There's some a e to the ikx, then some a star e to the minus ikx, and this is to be equal to 1. So now the exponentials cancel, and we just get a squared times the integral from 0 to L dx, and now we don't have this problem. It's not infinite. It's not a finite number. It's a very large number, but it's a number. And we find that a is equal to 1 over the square root of L. So the wave function k, the eigenstates, are 1 over square root L e to the ikx. Now they're normalized to a chronicle delta. If k is different, then because of the normalization condition, it'll cancel, right? Because it's a full period. And if k's are equal, then you get 1 over L times the integral from 0 to L over dx. That's what we imposed. So now it's normalized to 1. So this solves the problem. Put a product in a box and make the box really, really large. Of course, this can also be done in 3D. If you do this game in 3D, then your eigenstate, which is now 3 quantum numbers, so the vector k, which is kx, ky, kz, 3 quantum numbers, it's going to be 1 over L in 3/2 e to the ik dot r, where k is kx, ky, kz, and r is xyz. It's closed in 3D, where you have the box and you impose boundary conditions in all 3 directions. So if I go in this direction, this direction, this direction, I always come back to myself. That's what I was talking about when I went off topic. you put it all in a really, really big box, and you impose periodic boundary conditions. This is a trick which is used very often in physics and in quantum mechanics. Right, the main point is, I'll just write it down, the main point is now that the inner product is a chronicle delta. That's the point. Questions about this? No questions. Okay, I'm really happy I prepared a lot of small stuff. This way I don't run out of time because you guys are really quiet. Not even complaining at all. So another thing I would like to just cover in a few minutes, this will only take a few minutes, is something about this bracket notation. Something I never actually mentioned, but I think it's important. Something that somehow always falls between the chairs and when quantum mechanics is done. So let's consider an orthogonal basis, or orthonormal basis. And let's just, for illustrative reasons, just assume that it's not continuous. Okay, let's assume it's discrete. But of course, everything I'm going to say is also true for a continuous case. But let's just assume that this n is discrete, so you can only take the integer values, 1, 2, 3. It could be the eigenbases of harmonic oscillators, of infimum potential well, or hydrogen atom. Just imagine this n being 3 quantum numbers, and 11, just some orthonormal basis. Let's assume 1 quantum number for simplicity. So imagine a harmonic oscillator if you must. So you know that any wave function can be written as a superposition of these eigenstates. Now what are these ANs? What are these expansion coefficients? Well, they're the inner product of n with psi. Or the projection of psi onto n. It's like a dot product. In linear algebra, or an integral in if it's continuous, it's infinite energy space, but it's just a projection of psi onto n. It's important you note that. Because n is just a direction in space. It's not necessarily three-dimensional space, it could be infinite dimensional space, but it's just a projection of some vector psi on some base vector n. Right? In three-dimensional space would just be a cosine, for example, cosine of the angle between them. Now, how do you see this? So there's a very important relation that you have seen in your homework, but I'm not sure you actually realized the importance. And that's the fact that if you sum over all, first of all, you know that this is a matrix, it's an operator, right? If I sum over all of the eigenstates, then I get the identity operator. And you demonstrated this in three-dimensional space for your 1, 2, 3, and ABC states, if you remember, that this actually works, this actually is the identity operator. But this holds for all eigenstates in all dimensions. So if you sum over from n goes from 0 to infinity for all the harmonic oscillator states, and if you would actually do this, then you would get 1 in the end. So you take all of your harmonic polynomials and Gaussians and so on, and actually compute this. This is just a complex conjugate of that, right? And sum over all of this. It's mathematically very challenging, but in the end you just get the number 1. Just multiplication by 1, that's the operator. And this, of course, is a very helpful thing to note, because it can be used in all sorts of places to prove all sorts of stuff. And it's used very often in quantum mechanics to prove stuff by using just a bracket notation. These proofs and stuff gets very, very simple to use. So, for instance, I want to prove this. I want to use this statement or this statement using this identity. So I start off simply by saying that psi equals psi. That's obvious. I didn't say anything. And obviously, it's the same as saying psi equals 1 times psi. Right? I'm not really doing anything. But now I can insert 1 in this complicated way of saying it. And now this thing here is just a number. But usually I can't just move bras and cats around because the order matters. So I can't just move them around. But this thing is a number, it's the inner product, and numbers can be moved around. And now I can just go ahead and call this thing, give it a name, it's a number, right? Let's just call it AN, and we got there. So knowing this identity is very powerful for looking at different wave functions. Now another thing that you should note, a different board, if we're talking about bracket notation, is what does it mean? What does this projection mean? So if I write a wave function, psi, and then I'll put a bra of an x here. So it's the x, the position space eigenstates. What does this mean? This means I'm projecting the wave function psi into position space. So this is just what we used to call psi of x. In the same way, if I project into k space, this is what we always called psi tilde of k. For those of you who are reading Kontanoji, this is obvious. For those of you who are not reading it, big mistake, read it. It's about time. But these things are very helpful, are very handy. Let's see what we can learn from this. Knowing that this is just the projection of psi onto x, so it's the psi in x space. What does that mean for this inner product? It's the wave functions of k, the eigenstates of k, projected onto x. So what is that?
Commutation.
Excuse me? It's not a commutator. It's the. So I'll tell you again. It's the k eigenstates in x space. So it's just e to the ikx. Maybe I'll make this a little bit more implicit. Okay, I'll make it a little more obvious what I'm saying here. But let's try and look at this in the most stupidest way we know. What does this mean? This means we have to integrate, right, over the compass conjugate of the x functions. The x eigenstates are delta functions times the psi, and then we have to integrate over x. So this obviously is psi of x naught, right? Now just call x naught x and you get there. Right, so you understand why this makes sense. And now you understand why this makes sense as well. It's the k eigenstates, so the psi would just be phi of k, will be e to the ikx, so that's your e to the ikx in position space. Why is this helpful? Why do we need this? Say I know psi of x, it's given me. And I want to find psi of k. And I don't remember how to go from one to the other. It's a stupid example because we know it's the Fourier transform. But this could be also different bases where we wouldn't necessarily know it. So using this notation becomes very simple. Because this psi of x, we can write in bracket notation as the sandwich of x and psi. And now we can insert the identity operator in the middle. I didn't do anything, just multiply by 1. And if I multiply psi by 1 and then by x, or just don't multiply by 1, it's the same thing, I didn't do anything. Now I can write this one in a complicated way. How can I write it? So I told you that this one, in case of discrete states, it's the sum over n over all n states. But I can also write this for continuous, but this is discrete. But if it's continuous, then 1 is the integral, right? Sums become integrals over dk over all the k states. This will come very helpful. So let's write 1 as this integral. So we have x. Take the integral outside, so it's the integral dk x k k psi. Now look, integral dk. This x on k is 1 over root 2 pi e to the I kx. And this k on psi is psi tilde of k. I've proven to you that it's Fourier transform just using bracket notation. So that's why another reason that this identity is really, really helpful, and it should be your close friend. It's called the completeness relation. So this is only true if the basis k or the basis n is complete. So if you have a three-dimensional space, you have x, y, and z. You get only 2 unit vectors, it will be complete, it will be true. It's only true if the basis is complete. Questions?
Isn't that k and x functions specific for the free particles?
No, the eigenstates of the k operator are e to the ikx in position space. There are deltas in k space. The eigenfunctions of momentum, or the momentum operator, but momentum divided by h bar, right, is k. The free particle is just k squared, or k squared divided by some constants, so that they have the same eigenfunctions. But if you look at just the k by itself, it's just a momentum operator. These are the eigenfunctions. Questions? Okay, one last thing before I set you free, or before I send you to work even harder than you did all semester because you have a hard test coming up. I want to point out one thing which is also in your homework of this week, but I won't have time to look at it before. Well, I won't see you again, or maybe I will see you in a repetition lesson, but then I want to talk about the test. So one more thing I would like to talk about is when we compare Bohr and the Bohr model and the real quantum mechanics in hydrogen atom. So I'm going to plot what we know in quantum mechanics to be true. We know, if this is the energy scale, we know that at n equals 1, which is the ground state, there is one eigenstate where L and M both are 0. So the angular momentum sets above 0. For n equals 2, there are 4 eigenstates which are degenerate, namely 0, 0, 1, minus 1, 1, 0, and 1, 1. And then we go further up to n equals 3. There are 9 eigenstates, where the angular momentum states are these 4. And then the 2's. Right? And so on and so forth. Now, Bohr told us that there's only one state for each energy, right? There was no determinacy in Bohr's case. And there's only one quantum number. But he predicted the values of the energy, he predicted correctly. So the formula, right, the minus 13.6 electron volt divided by n squared for the energies, that is correct. That Bohr predicted very correctly, which is why it agreed with the experiment. Now, experimentally, people only noticed that this isn't true when spectroscopy experiments got more detailed, and we noticed that these states are actually not degenerate. As far as we know, they are, because we didn't actually talk about the hydrogen atom. We talked about an electron in a Coulomb potential. That's like the beginning of the hydrogen atom. As you know, electrons are spins. The nucleus is a spin. The electrons are traveling really fast, so it becomes relative speeds, relativistic speeds. So it turns out that these states are actually not degenerate. It's actually something called a hyperfine splitting. So that's something you're going to meet in your next quantum mechanics course. And then people notice that, okay, this state is not degenerate, then there must be more than one state which look degenerate if you're not looking carefully enough, which means there must be more than one state here. Another example I showed you was the magnetic field last week. Using a magnetic field, you can make this state and this state become different in energy than the zero states. So people notice that there must be more to it than Bohr just said. So the question arises, what did Bohr see? Which of these states did Bohr actually see? Did he see all of them? Did he look at a specific one? So this is something I asked you to analyze in your homework. The solution is that Bohr saw these outermost states. These are the states that Bohr actually saw. Why is that? Because Bohr assumed that the motion is a Kepler motion. Kepler motion is in the plane. Since when something moves in a plane, it only has one angular momentum component. So when he quantized, he called it L, but it actually was Lz, and he said that must equal NH bar. Now we know that Lz equals mH bar, right? We know it's h bar as an integer, but there's more to the story. There's also an L squared, because the motion is not in a plane, it can be anywhere in a sphere. And we know there's also a principal quantum number, which has to do with the radial quantization, right? The radial direction. But what Bohr actually quantized is this n. Now Bohr assumed that this n in Bohr's case must start with 1 and can't be 0. We know that it can be 0, but if we just modify Bohr a little bit and say, okay, let's start it from, let's say Lz equals NH bar and start n from 0. So this is Bohr. And this is modified Bohr. Then he actually sees these states, because here angular momentum, this Lz is 0, here Lz is 1, here Lz is 2. He just didn't realize that if Lz equals 1, he didn't realize that if Lz equals 1, I can also be up here because there are other quantum numbers. So he didn't even see the state. He just associated this Lz equals 1 state with this energy. So this is what Bohr saw, but we know the real story. Well, this is not the real story yet, as I told you. The real story is next semester, or next year. But until then, you have more difficult stuff, other stuff to focus on. So if there are no more questions, then I'll wish you good luck with the test. Be in contact with me for the equation sheet. Otherwise there won't be one, and well, your problem. So be in contact with me. I've already started, so it's going to be easy. And study hard, come ask me questions. If you would like a repetition class, then be in contact with me as well, and we can set something up. Okay, good luck.